Hello and welcome to our talk on Who Can Find My Devices. In this talk I will present our results from analyzing Apple's crowdsourced Bluetooth-based location tracking system called Find My. This was a collaborative effort between my colleagues Alex, Tim, Matthias and myself. Who doesn't know the problem? You left your smartphone somewhere, you cannot find your keys, or you don't know whether you left your notebook at work or whether it was stolen on the subway. Now, you can either search by yourself or ask friends for help. Or you could ask a global crowd for help. But what we are really interested in is offline finding. And what if we could locate every object in the physical world if we are authorized and even if the object is offline? This would be another step of the digital transformation in our society. Offline finding already exists in proprietary systems. Apple's Find My network, for example, claims one app to find it all. Specifically, Apple's system is able to locate devices that are owned by the same user, and since 2019 it also works when devices are offline. To implement this, Apple uses hundreds of millions of crowdsourced iPhones across the globe. And last but not least, Apple promises that the whole system is secure and especially privacy preserving. Now let's have a look at Apple's specific claims. For once, we can find Apple devices. Apple promises that it works for offline devices and that the entire Apple ecosystem helps with finding. And finally, everything is supposed to be secure, private and anonymous, and even Apple itself does not have access to any location information. The privacy implications of such a system are enormous, and Apple's promises sound too good to be true. So we decided to analyze the security and privacy of Apple's Find My system. In the first step, I will present how Apple's offline finding works. Then I will derive the possible risks and then present the solutions that Apple implemented. Our knowledge comes from a comprehensive reverse engineering campaign, as well as a few documents that Apple shares with the public. So, in this example, we want to locate this notebook. During normal operation, it is connected to the internet, and therefore it is able to send location reports to Apple's iCloud infrastructure directly, which we can then query from a second device. If the notebook loses internet connectivity, it can no longer report its own location, but instead it starts emitting special Bluetooth advertisements, and this even happens if the device is asleep, for example when you carry it in your bag in the subway. All devices in Apple's ecosystem continuously listen for those advertisements, and when receiving one, an iPhone for example determines its own location either via GPS or Wi-Fi tracking, and this location is actually an approximate location of the lost device. An iPhone collects several of such reports and regularly uploads them to Apple's servers. From there, the owner can retrieve location reports of their own devices. As privacy researchers, we can immediately make out a number of potential issues with such a system. For one, we want to ensure that lost devices cannot be tracked by others via their Bluetooth advertisements. Secondly, there is the issue that Finder devices disclose their own location to Apple's servers. And finally, since all data is centrally stored on Apple's servers, could Apple or a third party access the reports and learn the location of lost devices or Finder devices? Fortunately, there are several solutions to these problems. The first is to use unlinkable pseudonyms in the Bluetooth advertisements that change regularly. This will make it harder to track a lost device over time or to re-identify it across different locations. Second, we can submit location reports anonymously. And finally, we can use end-to-end encryption for the location reports. In this way, only the owner is able to decrypt reports for their own devices, and even Apple does not gain access to this information. So let's see how Apple implements the unlinkable pseudonyms. For every device that the owner wants to track, we need to generate a set of so-called master keys. In particular, the master keys consist of a public-private key pair on the P224 elliptic curve called D0 and P0, as well as a symmetric key as K0. The symmetric key updates itself every 15 minutes using a well-known key derivation function, or KDF, creating a chain of symmetric keys. These symmetric keys are used as seeds for the actual Bluetooth advertisements. To get to the advertisements, we first apply another round of KDF to each symmetric key to get two scalars. Finally, we use the master public-private key pair together with the two scalars to calculate the unlinkable public-private key pairs that are used for the Bluetooth advertisements. In fact, each Bluetooth advertisement encodes the public part of this key, and the private key can later be used to decrypt the encrypted location reports that are submitted by the finders. To implement offline finding, we need to put a 28-byte public advertisement key into a single Bluetooth Low Energy advertisement. According to the standard, an advertisement consists of a MAC address field and a payload of at most 30 bytes, so this should not be a problem. However, the Bluetooth standard also mandates that custom fields in the advertisements must be prefixed with a company identifier. In addition, Apple already uses subtypes for their advertisements, which only leaves 25 bytes for the key. As a solution, Apple repurposed the address field to encode part of the public key and the rest of the key in the payload. Still, we are not done, as the Bluetooth standard also mandates that the two first bits of a random MAC address must be set to 1. Therefore, the advertisement also contains those 2 bits as part of the payload. Now, whenever a Finder device receives a Bluetooth advertisement, it extracts the public key PI and at the same time generates an ephemeral public-private key pair on the same elliptic curve. The Finder then uses elliptic curve Diffie-Hellman key exchange to derive a shared secret. The secret is in turn used to derive a symmetric key and initialization vector. Using this key material, the Finder encrypts its current location as well as an accuracy value using AES-GCM and uploads the report together with a timestamp, the hash of the lost device's advertisement key, and its own ephemeral public key to Apple's service. The hash public advertisement key PI is used when an owner device requests a report for their own devices. Here, the owner submits a list of the most recent advertisement keys of their lost device so that Apple can deliver the corresponding reports. The ephemeral public key of the Finder is required so that the owner can derive the same shared secret using the Diffie-Hellman key exchange to be able to decrypt the location report. We conducted a comprehensive security and privacy analysis of the system's design and implementation, and this is what we found. So first of all, it is the first commercial offline finding system that has a privacy-first design, and it integrates the 3 discussed solutions. So Apple implements encrypted end-to-end location reports. It uses rotating public keys for the Bluetooth advertisements. And finally, it makes sure that Finder devices remain anonymous. However, at the same time, the system becomes rather complex, and this is typical for Apple. There's little public documentation about the system. And if something cannot be easily evaluated independently, errors might hide for a long time. In our work, we have discovered 2 distinct privacy vulnerabilities in Apple's Find My system. The first one allows unauthorized access to the user's location history by any local application running on macOS. So what went wrong here? To understand the vulnerability, we have to know that Apple's Find My service, as well as many other system services, use the secure system keychain. And Find My uses it to store master keys that are used to generate the pseudonyms for the Bluetooth advertisements. This process is computationally heavy, so Apple initially stored the pre-generated advertisement keys in a cache directory in the file system, and this directory was accessible by any unprivileged application. These keys in the cache directory could be used to download and then decrypt location reports for the user's devices, and therefore an attacker was able to access all location reports for the past 7 days for all the user's devices. And while Apple has meanwhile patched the issue, we assume that users were vulnerable to this attack for at least 1 year. Now, when we discovered the issue, we were interested to know how much an attacker could infer from the location reports, because there was no information available about how precise the Finder reports are and how many reports were generated in the wild. To this end, we conducted a set of experiments. First, we wanted to know whether and how precise we could track a victim's path. To this end, we used Apple's private download API to get location reports from our own devices. This is what we did. So during the experiments, one of the authors carried a lost iPhone through downtown Frankfurt am Main in Germany. And with the same iPhone, we recorded a GPS trace as a ground truth. And this is what we show on the map to the right. After the experiment, we downloaded and decrypted the offline finding reports via Apple's private API. And the raw location reports that were submitted by other Finder devices are shown as black dots on the map. These raw reports already matched the GPS ground truth data rather well, but we wanted to go a step further and see whether we could actually reconstruct the path. So we used a smoothing algorithm on the raw offline finding reports, and now we can see that our reconstructed path matches the ground truth data rather well. In numbers, we were able to achieve a mean error of less than 30 meters. In the second experiment, we wanted to know whether access to the location reports would not only allow us to track a victim, but to identify individuals by leveraging the so-called top locations. Those are the locations that an individual spends the most time at. To this end, one author carried an iPhone during a regular work week. After 1 week, we downloaded and decrypted the offline finding reports generated for this device, again via Apple's private download API. We then applied the dbScan clustering algorithm on the raw reports, which we interpret as the user's top locations. We show the clusters as well as the noise on the map to the right. For this talk, we anonymized the results by using a random projection to the City of London. Note that as a pre-processing step, we had to resample the reports on the time domain, because otherwise short visits to crowded areas would be overrepresented, as more Finder reports are generated there than, for example, in more remote areas. We also wanted to know whether we could not only identify the top locations, but also determine their type based on the visiting time pattern. On the right, we mapped the top locations to the hours of day that they were visited. We can assume that the topmost location is the author's home, as this is the only location that is visited during all hours of the day. Also, we can make out the author's working place, as this location was only visited during regular office hours. We verified the findings by letting the author label the locations. In conclusion, we were able to identify all top locations with an accuracy of approximately 10 meters, which according to related work would be sufficient to uniquely identify a person. I just explained the implications of the first vulnerability, but we also discovered the second one. We found that Finder devices tend to upload location reports in batches, probably to conserve both battery and bandwidth. This means that while Apple cannot decrypt the location reports, they could infer which reports have been made in close proximity to each other, assuming that Finder devices travel at finite speed. Secondly, we found that owner devices must authenticate with their Apple ID to be able to download the encrypted location reports. Together, this would allow Apple to build a social or proximity graph of owners. However, there are two caveats to this finding. Firstly, while it would be technically possible, Apple claims that they do not store the required metadata, and we have no evidence to disprove this claim. Secondly, constructing such a proximity graph would require owner devices to actively use the Find My application. Nevertheless, we find that this issue leaves a sour aftertaste to this otherwise well-designed system, especially since Apple has not commented on the issue after our responsible disclosure. Even worse, there would be a simple mitigation. Apple could simply drop the authentication requirement for downloading reports, because the authentication actually does not provide any additional security, at least based on our understanding of the system. So let's recap Apple's claims. The offline finding system indeed makes it possible to find Apple devices, but in fact also any other Bluetooth-enabled devices, which I will talk about in a second. And this indeed also works if the devices are offline. Unfortunately, the system is not fully anonymous by design, as it would allow for correlating user locations. Also, as with every design, the devil is in the details, or more precisely in the implementation. And finally, we also found that the location reports are in fact not only stored for 24 hours, but we were able to download encrypted location reports for our devices for up to 7 days in the past. To wrap this up, Apple's ecosystem is enormous. To analyze their proprietary system, we invested quite some time and energy to develop tools that helped us understand the system in detail. As part of this work, we implemented OpenHaystack, an open framework that allows for tracking the location of any Bluetooth device via Apple's Find My network. And it already has an unusually large user base on GitHub, so feel free to try this out. Based on our understanding, we then conducted the first security and privacy analysis of Apple's Find My system. We discovered two distinct flaws in this otherwise well-designed system. In addition, we provide first insights into the performance and accuracy of the generated Finder reports. Thank you for your attention. My name is Milan. Feel free to reach out to me or one of my colleagues if you have questions.